What's up? What's up? What's up? What's up? What's up? What's up? Hey, so today we're gonna do problem 2509, cycle length queries in a tree. This is a problem from the most recent competition batch. It's classified as a hard, but I'd argue that most people that are familiar with tree problems, with graph problems, would claim that this is more so a difficult medium, maybe. But like I've said in multiple videos, I don't want to continue to exhaust to this point. The classification system isn't always the most accurate. Some hards are medium, some mediums are hard, some easies are hard. But I guess that just really depends on your previous exposure to similar problems. This might be more difficult if you've never done a tree problem, but this is definitely more of a medium if you have, especially given the constraints. But anyways, let's go ahead and get right into it. So you are given an integer n. There is a complete binary tree with 2 to the n minus 1 nodes. The root of that tree is the node with value 1, okay? And every node with a value in the range 1 to 2 to the n minus 1 has 2 children, where the left node has 2 times val, and the right node has value 2 times val plus 1. So what that basically means is, like, if you have n equals 3, so n equals 3 would be the 2 to the n minus 1 nodes. So that would mean there's 2 to the 3, 8 minus 1, 7 nodes. So what would that system look like? You'd have the root. It would have 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes, 6 nodes, 7 nodes. So being complete just means that every node, unless it's a leaf, right? Every node, unless it's one of these bottom nodes, has a left child and a right child. So that the node is like a perfect triangle, right? It's a bushy, it's a thick, it's a wide tree, right? If I can't have a case where, like, this system has 1 node to the left, right? That's not complete. It would have to have these, in order for it to be the next level, right? It would have to have every node, unless it's a leaf node, would have to have 2 children, right? And they all have to be at the same level. And you'll notice that this is n equals 4, right? Because there's 2 to the 4 minus 1, 2 to the 4, 16, minus 1, 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Notice. So that's all it means when it says complete, right? But let's not prolong our focus on that point. So you're also given a 2D integer array queries of length m, where queries I equals ai bi. For each query, solve the following problem. Add an edge between the nodes with value ai bi. Find the length of the cycle in the graph, right? So if you have a tree, right, this is kind of like a discrete math concept, but if you have a tree, any edge you add will end up creating a cycle, right? Like if I connect this node to this node, right, it's going to end up creating a cycle. If I connect this node to this node, it's going to end up creating a cycle, right? So any path you create, any additional edge you add to a tree creates a cycle, right? Because a tree has everything connected. So everything's connected to everything, but there's no cycles. Well, if everything's already connected to everything, adding an additional node will make that thing have a cycle inside of it, right? Because if everything's already connected, so everybody can reach everybody, right? I can communicate with any of my friends through different friends, right? So if I add an additional link between 2 of my other friends, that means there's a redundant connection, right? Because I can already connect to A and I can already connect to B. So if B communicates with A, now there's a cycle between all 3 of us, right? Right, and I guess in a drawing, I don't know why I'm focusing on these points so much, right? If there's a person A, and the person A can, through some network, connect to person C, right? And through some network, can connect to person, that was weird, why did I do that? Connect to person B. This cloud just means there might be a million nodes inside of here. So if you connect C to B, well, I can connect to C already, and I can connect to B already, and now if B connects to C, that means there's a cycle, right? So adding any additional edge will create a cycle in the system. Okay, so this is basically saying if I add that edge, what's the length of that cycle, right? Because, like, when I added, a link from here to here, it created a cycle of 1, 2, 3, right? There's a 1, 2, 3, 4, a cycle of length 4 between these 2 nodes, right? and then remove the added edge between nodes with values AI and BI. So that's essentially saying we add the edge, we figure out how long the cycle is, and then we remove it. So each query is queried upon the original tree, right? When we add an edge to see what happens, we don't keep that edge in. We remove it and then solve the same problem. So we keep solving independent queries on the initial tree that we create. So we know what a cycle is, right? A cycle is just a path where you start somewhere and then you can find your way back to that somewhere, that starting point. There could be multiple edges between two nodes. Yeah, so like if you connected, right, in this problem, if you connected these two nodes to each other, now there's a cycle here of link 2, right? So let's look at this first example. So for n equals, is there another example? All right. Well, this is the idea of having two edges between two nodes, right? But let's not harbor too much on that. So let's look at this example here. So we have n equals 3, so we've already drawn that tree out, but let's just draw it again because I guess we can make it a little bit more clear how it's supposed to look. All right. Problem is when I try to make things really clean, I end up making them really bad. The secret is to not try too hard. Just try hard enough. Okay, whatever. You're not here for philosophy, but what is chemistry if not physics? And what is physics if not math? And what is math if not logic? And what is logic if not the study of the mind? And what is the study of the mind if the study of the mind is not biology? And what is biology if not chemistry? And what is chemistry if not physics? And what is physics if not math? You see where we're going? The cycle. Okay, so we have this system here. So then let's label these nodes. So we have 1, 2, 3, 4, 5, 6, and 7. Made those really small because I'm an idiot. Okay, so we have queries 5, 3. So if we have query 5, 3, that means that we connect 5 to 3. And then we figure out, okay, well, the cycle is here to here to here to here, right? And it has length 4. And then since each of these are independent, we then remove that added edge. And then we look at query 4, 7. So we add a link between 4 and 7. And then we connect 4, so that's 1, 2, 3, 4, 5. And then we do the same thing, right? So we remove this, and I think you get the point about how this works. So how would we find the answer to this efficiently? Well, I guess to look at the constraints, n is only going to be up to 30. So n is very small, right? N is very small. M is kind of big, right? M can be up to 10 to the 5. So it's okay if we do n operations for each of the m queries, right? Like that's what this constraint system is telling me, right? It's okay to do n operations for all the queries that we look at, right? Because that would just be n times m times. N is like 10 times 3, so 10 times 3 times 10 to the 5, that's 3 times 10 to the 6. So that's not that, that's doable, right? That's a feasible number of computations. So if we have an algorithm, right, just based on these constraints, right? If we have an algorithm that's O of n times m, that's going to be more than enough to pass, right? That's efficient enough. So if we look at each m queries, can we do something that takes O of n time? Remember, n is just the height of this tree. Sort of, right? It's proportional to that, right? Well, in order to find a cycle, what does that mean in terms of this tree if we thought of it in terms of where a node is with respect to other nodes? Well, in order for there to be a cycle between two things, they're going to go up the tree and meet at some point, right? In order for there to be a cycle, because this thing has a path to the root, right? Every node has a path to the root, right? So if I look at this thing's path to the root, somewhere along that path, the node that it has a cycle with has to intersect with it, right? If it has, let's look at 4's cycle with every node, right? So 4 has a path to the root. 5 has a path to the root. Oh, well, since they meet here, we know that if 4 was to connect to 5, we'd have a link like this. 2 has a path to the root. 2, well, since 2 is already connected to 4's path to the root, that means they'd have a link like this, of link 2. If we looked at 6, or let's look at 3, I guess. If we look at 3, 3's path to the root is here at 1, so that means they connect at 1. So if we created this link here, they connect at 1, so it'd have path 1, 2, 3. So the idea is, I guess, let's see if I can think of this more generally. Right, if there's 2 nodes that we're trying to connect, if we have this tree has a root always. Right, and I'm trying to connect node X with node Y. Okay? Somewhere, X has this path up to the root, whatever it looks like, I don't know. Right? And Y also has some path up to the root. I don't know what it looks like. If at some point, those two things have to merge in order for these things to create a cycle, right? Because X and Y create a cycle because there's some place where they meet with each other, right? So if I was to connect X and Y here, right? At some point, these things would have to meet across X's path or Y's path. So if I calculate X's path to the root, and then I try to connect Y to it, at some point, Y is going to merge with X. And at that point, I would just say, okay, what was the distance for X to get here? And what was the distance for Y to get here? And this is an added edge length of 1. So I just find the first place where these two things merge. Right? I find the first place where X and Y on their path to the root meet each other. I find how long it took X to get there in terms of how many edges it had to traverse to get there. And I find how long it took Y to get there. So how many edges Y had to traverse to get there. And then I just add 1 for the connection between them. Okay? So if we look at this example here, okay. So if we look at this example here, and let's look at one of the queries. So if we're connecting 5 to 3. Okay, so we're connecting 5 to 3. So let's calculate the distance to each node for 5. So if 5 wants to go to 5, that's going to cost 0. That's going to cause 0 edges, right? Because there's no distance for 5 to go to 5. And then if 5 wants to go to 2, that's going to cost 1, right? It's going to have to use 1 edge to get to 2. And then if 5 wants to get to 1, that's going to cost 2. If 3 wants to get to 3, that's going to cost 0. And if 3 wants to get to 1, sorry about that. To make a long story short, my wife's concerned about me because yesterday I was at the gym and these two let's just say they're not Albert Einstein, these geniuses, right? So I'm at the gym yesterday, I'm doing planks, getting ripped, getting shredded, and my head's extended out while I'm doing planks. Near me, maybe 6 feet to my right, 2 MIT grads, they're idiots, were using a weighted ball and throwing it to each other, and somehow one of them slipped when they were throwing the ball, and a 20-pound weighted ball comes flying and boom, hits me across the head. Likely had a minor concussion. My IQ was dropped several points. Fortunately for me, I'm so smart that I can afford to lose a few points. I'm just kidding. So my wife's all worried about me and calling me. But anyways, that's besides the problem. So in order for 5 to get to 1, it costs 2. In order for 0 to get to 1, it costs 1. So then this is the point where they meet, right? So since they meet at this point, it's going to cost 5, 2, and it's going to cost 0, 1 to get to the point where they meet, and then an additional 1 to connect them. So that's 2 plus 1 plus 1 equals 4. All right, now let's look at an example which is a little bit, I guess. Okay, so all of these include the root. So what if you had something like this? What if you wanted to know how long it would take for 5 and 4 to meet, for example? Okay. So we do the same thing for 5, right? So we'd go down this path, and we'd find that it takes, 0. It takes 0, 1, 2 to get to the root. And then we play the same game for 4. So it takes 4, 0 to get to here. And then it takes 1 to get to here. And then this is at the point, see, they've already met, right? 5, we would track that 5 has already been to 2. So since 5's already been to 2, we know that this is a point where they could meet. And then I'd ask both of them, okay, 5, how long did it take you to get to 2? It would respond, it took me 1 second. Then I'd ask 4, okay, how long did it take you to get to 2? And it'd say, okay, it took me 1 edge, not 1 second, sorry. And then I'd add an additional edge between these two to connect them, and that takes 1. So that'd be 1, 2, 3, which makes sense, right? Because there's a length 3 path between these two nodes. Okay, so how are we going to do this efficiently? Let's just go ahead and get right into it because I'm taking a long time to articulate this problem. So we're going to look at each query, right? So we'll say for A, B, and queries. For one of the nodes, we'll keep track of how long it takes for it to get to the root, right? So we'll find one path to the root for one of the nodes. That will take n time, right? It'll be proportional to n, right? And then we'll look at the other node and find when it intersects with the first node's path to the root. So to efficiently find the first person's path to the root and save that information in a way so it's easily and efficiently accessible from the other node, we'll use a hash table. So we'll say length equals 0. And path of A, I guess. So the length is 0 and path of A will be a dict. And then we'll say while A doesn't equal 0. Because notice we can find someone's parent just by dividing by 2, right? 4's parent is 2. 2's parent is 1. 5, if we floor divide by 2, we get 2, right? 6, if we floor divide by 2, we get 3. So if we divide a node's value by 2, if we floor divide the node's value by 2, we'll always get the parent. So while we're not 0 means that we just looked at 1 and we got 0, so we've traversed the whole system. We'll say, okay, the path of A to A equals length. That's how long it takes to get to that node. And then we add 1 to length. And then we set A to A's parent by floor dividing by 2. Okay? All right. And then, so now we have path of A. So if we print path of A for each, the problem is it's not going to, okay, so let's just do that. So let's print path of A so you have that information so you can see it. So it's going to do this for each query. So we're kind of repeating information, but path of A is not defined because I Forgot to capitalize. All right. So we got, for the first thing we had 5. So 5 to itself has length 0. To 2 it has length 1, and to 1 it has length 2. 4 to length to itself has length 0. To 2 it has length 1. To 1 it has length 2. And then so on and so forth. So I'm kind of wondering if we should do this for each node. Nah, it's fine. The runtime is safe. There's probably a little bit of a tweak to make this just a bit more efficient, but I'm not concerned about it. So we'll find the path of A to the root. So we'll get that path and the length of that path. And then we'll set length to 0 again. And then we'll see how long it takes for B to go down its path and intersect with the path of A. So we'll say while B not in path of A, we'll say B equals B divided by 2 and length plus equal 1. And then by the end of it, so we'll have a return solution. So eventually B will be in the path of A. It could happen at the root, right? But at some point the paths will intersect. Then we'll know how long it took to get to B using length and how long it took A by using path of A. So we'll say return append. Well, we'll have the length. That's how long it took B to get to the intersection point between A and B. And then path of A at B. That'll be how long it took A to get to this point, to this intersection point. And then we'll add 1 because that's the length of adding an additional edge between them. Okay. And then at the end, we'll just return. All right, and then let's submit that. All right, so that's good enough for me. So what's the time and what's the space? So for time, we have to look at each M queries. So let's say, okay, so let's say M equals length of queries. Okay, and then we already know N is here. So for each N, we have to look at each N queries, right? And then for each N queries, we have to go to the root. We could end up, in the worst case, going to the root twice, right? Because these things only intersect. If 2 nodes only intersect at the root, I have to travel up this entire node's path to the root and then travel up this other node's path to the root. So that's going to give us 2 whole paths to the root. So how long could that take? Well, it's proportional. The height of the tree is proportional to N. So that's just going to take N time to get to the root from one node and N time to get to the root from the other node. So that's going to give us 2N time, right? So this could take N time and this could take N time. So that's proportional to N. So there's M queries, and then we have to look at each N. For each query, we have to look at a path to the root, which is going to take N time. All right. And then for each query, we have to, for space, we have to return information about each query. So that's going to take M space, right? Because we have to create an element in this array for each query to return information. So that's going to take M time. And then for each query, we recreate a new path of A, right? Where we find out how long it took this thing to get to the root. So that's going to take N time, N space, right? Because we create that entire path, and that entire path could be the length of the tree. Or not the length, the height of the tree. So that could take N space. And yeah, so this is M times N time and M plus N space. You could pre-compute, right? So you could pre-process the tree, I guess. And you could find all the path of A's. Right, and there's that could get really bad, right? Because that wouldn't save you that much time. And there's 2 to the n minus 1 nodes. So you'd have to do 2 to the n minus 1 like calculations to pre-process every node's path. And then that wouldn't even save you that much time because you would pre-compute this information, but you would still have to compute this. So it wouldn't really save you on time that much. So I don't really even want to kind of investigate that. I think this is fair. It passes. It's good. We're good. All right, guys. Have a good day.